I hope you're fine. This is our lecture number 15, and we will continue further as I was talking about. This topic is related to some of the topics which we actually going to study in this. We have absolute temperature and then thermal expansion and some more topics related to that. So let's continue with this. First thing is, what is absolute temperature? That's important. When you say absolute temperature, remember that absolute temperature is everything to do with temperature scale, right? When you say temperature scale, now what exactly is the situation in that? When you say temperature scale means the temperature, the scale we are actually talks about. So remember that there are basically three temperature scale, but we will talk about only two temperature scales as they are a part of our syllabus and all. So basically, what exactly are the scales? One scale is called a Celsius scale, and the other scale is called as, in that case, the other scale is basically, uh, you can say Kelvin scale, the one we are talking about. Now, how the things are. For that, we need to go through some very basic information, which we will going to do. How? This is a thermometer, we have it, right? And when you take a thermometer, you put a mercury into that. There is a reason behind it why we take a mercury, because mercury, once it contact with the object here, anything, it moves linearly in the above column, right? Now, interesting fact is, if you take some ice here, right, and you start heating it up, right? So when you're heating it up, what happened? What we have noticed, let's take this thermometer without any calibration or anything. We have seen that as soon as we start giving it a heat, right, it will reach to this point, and after that, the mercury will not rise until all the ice converts into liquid form. We marked it, right? And once it becomes liquid, then after some time, definitely the temperature start rising, means the mercury goes up, 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 up. And once it reaches to this point and water start boiling, now temperature is not rising, and we mark this point as well. Now, this point is considered as lower fixed point, and that point is considered as upper fixed point. Now, everything is in between these 2 points. Celsius came in and he calibrated this lower fixed point and upper fixed point, and he divided these 2 points into 100 divisions, where one division is equal to 1 centigrade. Now, what is that lower fixed point? Lower fixed point is called as the melting point. And upper fixed point is called as boiling. Now, what is melting point and what is boiling point? Melting point, you see yourself that you start giving temperature, ice become liquid, right? So basically, at which solid state converts into liquid state, that melting point is a point basically. What is the situation here? That you can think of it as we already know that this is a mercury, and mercury is just reached to one point, and we mark it as a lower fixed point, upper fixed point once the water start boiling. So, but what is that point? That point is a point which is called as a lower fixed point. This is a point we called it melting point. Now, what is important about melting point? A temperature at which solid changes to liquid state without changing the temperature. This is very important. The temperature is not changing. Whatever heat you are providing at this point, that will be used to break the bonds of the solid, or you can say to change the solid state into liquid state. And once all the solid become liquid, then the temperature start increasing. And once you reach to this point and the water start boiling, you can say boiling point. And that boiling point, it's a temperature at which liquid converts into gas state without changing the temperature. So there is a melting point, there is a boiling point. Now within this period, within this, that within this, we divide it into, if Celsium comes up, it divides it into hundreds equal division, where one division is equal to 1 degree Celsius. So he puts melting point at 0 degrees, while boiling point at 100 degree Celsius. So in case of Celsius scale, you have a melting point at 0 degrees, while boiling point of water at 100 degrees. Now the next is kelvins. That is the second uh, degrees. And that Kelvin scale is also called as absolute temperature as well. Now, what exactly is the situation? Important part is what we have seen that hypothetically, remember that Kelvin has seen that at negative 273 degrees Celsius, as scientists, we believe that the gas has no kinetic energy, so it ceases to move. The particles cease to move at that degree. So it means that you do not have any temperature lesser than that. So hypothetically, this is the minimum temperature achieved for any gas, hypothetically. Now, this 273 degrees Celsius is that hypothetical temperature. So Kelvin started his scale from 0 degree Kelvin at that point, and that minus 273 degrees Celsius, which is 0K, is the temperature which we believe is the absolute zero, where the kinetic energy and the movement of the molecule cease to exist theoretically. So the scale which started its zero from that minus 273 is called as absolute temperature. Now, for simple melting point, the water has a melting point of 273 K, and the boiling point is 373 K. Excuse me. So this is the temperature scale. So what is Kelvin? Is a temperature scale or absolute temperature scale at which the hypothetical temperature, which is negative 273 degrees Celsius for any gas, especially we call it an ideal gas, which doesn't exist, at which if you take zero, if you place zero, that temperature scale is called as Kelvin degrees. So Kelvin is like this. Now, very important one thing. If you want to convert Celsius into Kelvin, you have to add 273 into that. Like, for example, if I ask you to convert 40 degrees Celsius into Kelvin, how do you do this? 40 plus 273, it will provide you the answer. Like in this case, the 303, 313. So 313 K will be the temperature in kelvins. All right. So this is the small bits and pieces related to absolute temperature and Celsius and melting point and boiling point. Now remember that because there is a property which we are saying is called as thermal expansion. Now, thermal expansion means it's a property that by giving heat, right? By giving heat, the object expands, especially if you talk about the gas, they expand. Now, how to do this? It's very simple. That when the material is heated at a constant pressure. Now, remember that we have to have, if we want to see the different relationship, in this case, you keep the pressure constant. So you've seen this. If you increase the temperature, the volume also increases because particles are taking enough kinetic energy from the heat energy and they start expanding up. So it means that temperature is directly proportional to the volume. Now remember that that temperature scale is a Kelvin scale, right? So expansion happens why? Because molecules start to move around faster as they gain kinetic energy. And this causes them to collide with each other and also with the walls of the container, right? So this is what we called as thermal expansion. Now, thermal expansion in terms of particles needs to be understood because definitely we've got three matters, solid, liquid, gas. What are the impacts, right? So in case of solid, it tends to expand the least. Why? Because the particles are very close to each other. And once you provide the heat energy, they expand the least at constant pressure. Then you have gases, they expand the most because the particles are already far away. There are enough gaps, intermolecular spaces between them. Then you got liquid. In liquid, it's between, solid and gases, right? So you can simply say that in case of solid, they expand more. Why? Because low energy molecules cannot overcome the intermolecular forces, attraction holding them. So basically, solid expand slightly because intermolecular forces are enough. In case of liquid, they are in between solid and liquid, so they sometimes overcome, sometimes don't, but they are in between. Their you can say tendency of expansion is in between solid and gases. While gases they expand significantly because they do not have intermolecular forces between them, so they like easily can overcome the forces of attraction holding them and simply expand. Now, uses of consequences of a thermal expansion. Application. The best application is in the thermometer. The thermometer is the best application, especially liquid in thermometer. In liquid in thermometer, you can say, I already give you an example of there is a mercury you placed there. And as soon as mercury is strike with the hot object or some heating material, the mercury start expanding. Why it start expanding? There is a reason for that. Because it start expanding because the molecules gain enough kinetic energy and they start moving up. Okay. It's in the liquid. So this is one of the applications of liquid in the gas. Okay. Now next is temperature activated switch. Now, temperature activated switch, the best example is a biometallic strip. You heat it up and it start expanding. It consists of two metals that expand at different rates and bends by the predictable amount at a given temperature. This is one of the examples, or you can say this particular thing, which are used in a practical, practically. So the best examples what we can give is in metal railway tracks, road tracks, and bridges. If you see them, there is always a gap while you see the tracks for the car, tracks for the trains. There are always a gap. One, you know why? Because we know that metal will expand while there is a heating. So they've given enough space so that they will expand. If you don't give them enough space, then the that metal track will damage early. So that particular thermal expansion is a property that is used over there. Now, let's talk about some energy thing, which is very, very important in this case. What is internal energy? Internal energy, as the name suggests, is the energy within the substance, and it rise of temperature of an object increasing the internal energy. Normally, internal energy is a sum of kinetic energy and potential energy. Both will add to give you internal energy. In the case of any particular solid, liquid, or gas, the total energy is stored inside a system by a particle that makes up the system due to their motion and position. Because position is changing, potential energy comes out. If velocity is there, then there is a kinetic energy. So technically speaking, if I talk about the kinetic energy, the heat energy will increase the movement of the particles, like they have getting the enough kinetic energy to start moving or vibrating. And once they have their vibration increase, their velocities increase, means kinetic energy increase. And plus their position also changes. So both kinetic energy and the potential energy will be increased in this case. Means total internal energy of the system increases. Like you can see here, check this out. You have a gas particles molecules here that are free and have intermolecular forces. Now we are specifically talking about the gases. But as soon as you give heat energy, they will further go, they strike themselves, they strike with the walls of the container. So what happened? The gas molecules much fastly moving, and they have kinetic energy, as well as definitely they have potential energy as well. So high internal energy and low internal energy without heating. All right. Now next is specific heat, which is very, very important thing. And what is a specific heat? Now, a specific heat is a special property that relates to different objects. First of all, the important part is, first of all, remember that a specific heat or a specific heat capacity is what? A specific heat capacity is, the formula is Q is equal to mc delta T. So C is equal to Q upon m delta T. Now what exactly it is? Amount of heat energy required to increase the temperature of 1 kg of substance, liquid, solid, gas through 1 degree Celsius, Fahrenheit, or Kelvin. There is another temperature here, Fahrenheit. So I just said it. Okay. The unit is what? Joules per kgs centigrades. This can be the answer. Now, this is what the formula is, and this is what the unit is. Now, if you check it out, the capacity heat capacity, this is copper, aluminum, and water. And if you check it out, the specific heat is increasing from left to right. The copper has the least specific heat, then aluminum has the second number one, and the water got the 4,200 joules per kilogram centigrade. What does it mean? That amount of heat energy required to raise the temperature. So if you're rising the temperature through 1 degree Celsius, that rise in temperature, just 1 degree rise in temperature for 1 kg of mass is basically a specific heat, right? So a specific heat moves from left to right. So you can think of yourself in case of solid, liquid, and gases, what will be the specific heat? It depends, right? So if you calculate it, this is the formula, you have it. Delta E means either you can say amount of heat energy. Here they give you as a delta E, which is change in energy. M is a mass, and delta Q is the change in temperature of the Celsius. Okay. So important part is this one. All right. Now important thing is, see, the point is water of mass 0.5 kg. So mass is equal to 0.48 kgs, and increase the temperature by 0.7. This is the change, right? 0.7 degree Celsius. So what is the specific heat? So what they are asking you, water of mass, this specific heat is that. Now, how much energy is required? Definitely, delta Q. So what is the formula? Delta Q is equal to mc delta T. Mass is 0.48. Rise in temperature, we will do that afterwards. Change in temperature, they already give it, 0.7. So, to calculate that, you simply need to put the values in and you get the answer, which is 0.48 multiplied by 4200 multiplied by 0.7. It's 1411.2. 1411.2 joules. This is the energy that is required to, that is the energy that is given, right? To increase the temperature through, temperature change of 0.7. So this is the amount of heat energy required. Now, one more thing which is there, which is very, very important is you can see that this is a graph that is shown. Initially, what happened? It's a solid state. Temperature is there. It's rising. Then temperature stays the same way. There is a melting because temperature doesn't change. Whatever heat energy required is required to change the state from solid to liquid. From here, it's solid to liquid. Then once it becomes liquid, then the state changes. Once it reaches there, now this is a point where the boiling is. We already talked about that. Boiling is a temperature where it doesn't change. It's just changing the state, but the temperature remains the same until all the liquid changes into gas state. All right. So this is what the graph between the time and between the uh, time and the temperature. So this is what our topic is all about, right? Now, point is very simple. Just for a second. So basically, it's between, we understand in this class, we have completed our solid, liquid, gases thing. Plus, we do melting point, boiling point in that. And we have done one more small topic is that there is a process called condensation or solidification. Now, what exactly it is? Condensation means when a gas cools, energy is transferred away from the system and kinetic energy decreases until temperature reaches to boiling point. So technically what happened in condensation? So condensation, the gas has condensed and it is now a liquid. It's a reverse process. Rather, liquid goes into gas state. Here, the gas comes into liquid state. Okay. And so it's a totally reverse process. As the energy has been transferred away from the potential store of the particle, the energy in the kinetic store is unchanged and temperature remain constant throughout the process. Solidification. Now, when a liquid cools, now it's from liquid to solid. It transfers away from the system and kinetic energy decrease until temperature reaches to the melting point. So you're going backwards. So liquid has solid and it's now in solid. So as the energy being transferred away from the potential store of the particle, the energy in the kinetic store is unchanged, so temperature remain constant through the process. So this is what the condensation is. So they are totally the reversed of what we have studied, like boiling and you can say all the things. Now we have already talked about that boiling. Boiling is what? When the liquid converts into gas state without changing the temperature. And what is melting? When solid state changing into liquid state without changing the temperature. Process is that. Now, there is a very small thing which we have to discuss here. Mostly students are confused between the boiling and evaporation. There is a huge difference. First of all, remember that boiling is a forced process in which you are providing heat energy. While in evaporation, that occurs at any temperature. Like if you placed it in a hot weather evaporation may occur. So it happens at all temperature. And second important part is boiling occurs all over the liquid, while it occurs on the topmost surface, right? On the main, the above surface of. Second, you can simply see what happened once the energy is being given at the top, right? So particles or molecules which are gaining enough energy, they comes out of the liquid as a gas state, and what left behind are the particles or molecules having less kinetic energy. All right. So what happened? Molecules and liquid have a range of energy. Some have lots of energy and other have very less. Their average energy related to the temperature of it. So what happened? More energetic molecules moving near the surface of liquid have enough energy to escape, and left behind the molecules having less energy. So this is the process of evaporation. The most important part is, in case of evaporation, there is a cooling effect because the particles which are left behind are cooled, or you can say less energy than the ones which are already gone. Now, what are the factors of that? Definitely, it depends on the temperature of a liquid. Increased temperature increase the kinetic energy of the molecule. So molecules with more energy are more likely to overcome the intermolecular spacing, holding in the liquid state and escape the surface. So more temperature, more evaporation. Surface of area. Greater the surface of area, greater will be the evaporation. Air movement. If air carries away water vapor which has just evaporated, this replaces the air above the liquid with a drier air which accept water vapor more easily. Therefore, increase air movement will increase the rate of evaporation. We already talked about this, that what exactly happened once this evaporation occurs. After evaporation, there is a cooling process. Because what happened, as the particle having more kinetic energy, they are going out. What left behind are the particles having less kinetic energy. So this process is used as a cooling process as well. The process of evaporation can be used to cool the things down. As evaporation occurs, the liquid cools. This because the most energy particle leave, reducing average kinetic energy, and placing an object next to this liquid cools the object. All right. So here we end up the lecture. In this lecture, we have covered up expansion, thermal expansion, plus we also covered up some boiling point, melting point concept, evaporation, boiling, absolute temperature, some more concept related to that, factor related to evaporation. And in the next class, we will see about the moods, which will be our 16th lesson. And we will talk about the moods of the thermal process. Okay. And let's see what further we will study in that. So hope to see you soon in the 16th lesson. Thank you very much. And it's end from my side. Bye.